All right, welcome back. Work and energy. I grabbed some problems from another textbook that at first glance looked good to review and demonstrate the concepts of work and energy and impulse and momentum with you. We're still on work and energy. I don't often memorize how to solve problems, so I really haven't read this problem. I only read it enough to say I'm pretty sure this should be straightforward. And what I like about this problem was that the force is not constant. It's a function of the position. And it makes sense. These sort of things, right? The more you compress a spring or extend a spring, the harder it gets. And the same thing here. Here it's not a spring, it's a bunch of barrels probably filled with sand or water or something that will absorb the impact. And the more you crush them, the stronger the force is. So the force exerted on the car by a prototype crash barrier as the barrier crushes is negative. That's the force on the car. 120s minus 400s cubed, where s is the distance in feet and the force is in pounds. The effective length of the barrier is 18 feet. How fast can the 5,000-pound car be moving and be brought to rest within the effective length of the barrier? And doesn't ask anything about time. It has distances there. I think I can solve it with F equals ma, but because it's a position sort of problem, I'm thinking work and energy. And so I start with the equation 1/2 mv1 squared plus the work put into the system is equal to the final kinetic energy, 1/2 mv2 squared. I'm gonna, the car has a weight of 5,000 pounds. The initial velocity, let's see, so m is 5,000 pounds over 32.2 feet per second squared. Pounds over feet per second squared is the same thing as pound second squared per foot. Pound, I didn't want to draw, I don't want to erase much, but I didn't want to draw an equal sign there. I just wanted to write the units. Pound second squared per foot, aka also known as a slug. And I'm off the sheet. I'm back. So I know what the mass is, 5,000 divided by 32.2 slugs, or pound second squared per foot. V1 is what I'm supposed to solve for, right? How fast can it be moving and be brought to rest? So it has to be brought to rest. V2 has to equal 0. So that's going to make this second term 0 all the way along. And then the force so it's going to be minus, just thinking what I want to write in here. I think I just want to leave it as variables. 1/2 mv1 squared, known, trying to find it, plus the integral. This is minus, that's a strange way to put that. The parentheses are there, so I'm going to say it's minus 120s minus 40s cubed ds from S1, which is here, and equal to 0, to here, which is S2, equal to 18 feet. I'll just write S2 for now. And so I need to integrate that. That's going to be equals 0. I'm going to move it to the other side of the equation at the same time. V1 squared equals, integrating the negative, they're going to become positive on the other side. This is 120 s squared over 2, so that's plus 60. Negative 120 s squared over 2. 120 over 2 is 60. Negative 60 becomes positive 60 on the other side. And then this is s to the 4th over 4. So that's going to be minus 10. It's going to become plus 10 s to the 4th. I'm going to evaluate that from 0 to 18 equals now this term here is pounds. That term there is pounds. When I multiply it times 18 feet, it's going to be pound feet. So we know what the units are on this here. That's going to equal 18 squared times 60 is a big number. 19,440 pound feet plus 18 squared. That's 18 times 18. And so I'll just square that again. That'll give me 18 to the 4th. Plus, that's 18 to the 4th times 10. It's going to be 1,049,760 feet. I'm going to double check that. 18 raised to the 4th equals times 10. And because they're all integers, I just left it at that. Probably 1,050,000 would be fine. I'm going to add to that the 19,440 and call it 1,069,000. But I think I'll keep going with the rest of this. So getting rid of the m and the 2, v1 squared is equal to 69,000 pound feet times 2 to get rid of the 1/2 and divided by m, 5,000 over 32.2. Remember, this is pound second squared per foot. And when I divide pound feet by pound second squared per foot, I'm left with feet squared per second squared, and the pounds cancel out. Right? So on my calculator, I will make sure I'm double checking the screen, make sure you can read it. Times 2 equals that. I'm going to store that. and I'm going to do 5,000 divided by 32.2 equals, that's what the denominator is. I'll inverse it to bring it to the numerator, and I'll multiply that times my 2 times 1069,000, which is that, and it gives me 13,771 feet squared per second squared. V1 is equal to square root 117, let's leave it at that, feet per second. That is correct, and that's around 80 miles per hour. F equals MA. I wish I had a timer so I knew how long the video was. S equals S0 plus B0T. No, that's not what I want. V final squared equals V initial squared plus 2AS. V final is 0. V initial is, no. V final is 0. V initial is unknown. So A and V are unknown. The acceleration is not constant. So you got to think through these. Do not use these equations. The force is not constant. The force is not constant, and therefore the acceleration is not constant. We cannot use these equations at all. We can say F equals MA, so MA equals minus 120S plus 40S cubed. Maybe this will work. Here's the problem where I have to think for like 5 more minutes before I figure out F equals MA solution. I'm sure it's not that complicated for this one here. But look, it was very straightforward. You were probably getting bored as I was going through it. It was so straightforward and easy. So I think I'll just end it there.